Hi folks, Dr. Chapman here. Today we'll visit Mesa Verde National Park and discuss depositional environments and foreland basins. Mesa Verde National Park in southwest Colorado is home to over 600 cliff dwellings that were built by the ancestral Pueblo people around the year 1200. The majority of these cliff dwellings were built into the cliff house sandstone, which is the uppermost formation of the Mesa Verde group. Formations are the primary unit used when formally subdividing stratigraphy or making a geologic map. They can be anywhere from a few meters to a few kilometers thick, and they are usually named after a nearby geographic location. It is somewhat outdated now, but historically formations were given a rock name when they were composed of a dominant lithology. For example, the Cliff House Sandstone is the same thing as the Cliff House Formation, and it was named after the cliff dwellings in Mesa Verde National Park. Non-geologists often mistakenly but innocently call outcrops formations, as in that formation over there looks like a hedgehog.
Did you see it?
Well,
Formations are lumped into groups and occasionally groups lumped into supergroups. Groups and supergroups often cover very large geographic areas, and the formations and formation names within them change from location to location. The Mesa Verde group, named after Mesa Verde National Park, extends from Montana to New Mexico, whereas the Cliff House Sandstone nomenclature is only used in the Four Corners region. Besides the Cliff House Sandstone, the Mesa Verde group at Mesa Verde National Park contains the Menifee Formation and the Point Lookout Sandstone. Beneath the Mesa Verde group is the Mancos Shale or Mancos group. Anytime sedimentary rocks are present, geologists ask themselves a series of questions.
And you may ask yourself, am I right? Am I wrong?
One question is, what depositional environment do these rocks represent? Interpretations of depositional environment are based on the principle of uniformitarianism. This principle presumes that the geologic processes operating today are the same as they were in the past. That is, they've been uniform throughout time.
They just love the uniform.
For example, if geologists find a sandstone with similar composition, texture, and sedimentary structures to modern beach sand, we infer that the sandstone was deposited in a beach environment in the past.
Seems reasonable.
Geologists often refer to rocks deposited in a specific environment as a facies, so we might refer to a collection of strata as a beach facies. There are hundreds, if not thousands, of possible depositional environments and facies, but a good introduction to them is to imagine a river making its way from the mountains to the sea. Within or close to the mountain, streams or rivers transport a mixture of sediment, including coarse sediment, like cobbles or boulders. These might get deposited during a large flood, and the resulting rock type would be called a conglomerate. As sediment is transported farther down the river, the clasts are worn down, broken into smaller pieces, and sorted by size. As the river approaches the shoreline, sediment may be deposited in coastal features, like marshes, estuaries, deltas, lagoons, and swamps. These depositional environments usually contain lots of organic material, like dead plants, and is where rocks like coal originally form. When the river reaches the sea, the water velocity drops precipitously, and most of the sediment gets dumped near the shore.
Just dump it in the ocean.
Waves rework sediment near the coastline to form beaches or barrier islands, and finer grained sediments can be carried farther away from the shore by currents and waves. Only very fine grained sediment, like clay or mud, is transported very far from the shore.
Well done!
And it too eventually settles out of suspension and ends up forming rocks like shale. At any given point in time, sedimentary rocks are being deposited in all of these depositional environments more or less at once, and they're collectively called a depositional system. In Mesa Verde National Park, the Mancos Shale was deposited offshore in a deep water marine environment. Overlying and gradational with the Mancos Shale is the Point Lookout Sandstone that was deposited as a beach and as nearshore sands in a barrier island system. Above the Point Lookout Sandstone, the Menifee Formation was deposited in a coastal marsh or swamp environment and contains thin coal layers. This pattern of transitioning from offshore to beach to marsh facies as we go up stratigraphic section tells us that the relative sea level was dropping, called a regression. The Cliff House Sandstone was deposited in a shallow nearshore environment, so the transition from the coastal Menifee group to the nearshore Cliff House Sandstone records a relative sea level rise, called a transgression. Outside of the national park, even younger stratigraphic layers are exposed, and we know that the Cliff House transgression was short-lived and the overall pattern was one of regression and relative sea level lowering. We call it relative sea level because the actual sea level elevation may not be changing at all. It could just be the land surface moving up or down. If you follow the Manco Shale to the west into central Utah, you'll eventually encounter age-equivalent shoreline beach deposits. As the shoreline moved from central Utah to southwest Colorado, it was depositing beach sandstone all along the way, resulting in a regionally extensive sheet or layer of sandstone. When the shoreline reached Mesa Verde National Park, it deposited the Point Lookout sandstone. As the shoreline migrated past Mesa Verde, it deposited the Menifee Formation. The vertical succession of sedimentary facies tells us what kind of depositional environment existed at that specific spot in the geologic past. It also tells us what kind of facies were present laterally, tens to hundreds of kilometers away. This concept, using a vertical sequence of facies to understand lateral changes, is called Walther's law, and it's a really powerful tool for interpreting depositional environments. Another major question geologists ask about sedimentary rocks is why did they accumulate in this location?
Not a day goes by I don't ask myself the same question.
Sediments don't pile up for no reason. There has to be a sedimentary basin to collect and hold them. The type of basin the sedimentary rocks exposed in Mesa Verde National Park were deposited in is called a foreland basin. Foreland basins form when the lithosphere is flexed downward by the weight of a mountain range, like standing on the edge of a diving board. The mountain range that formed the foreland basin is the Severe Thrust Belt, which extends from Southern California to northern Yukon Territory in Canada. A flexural depression formed in front of the thrust belt, sort of like a moat.
Lower the drawbridge! What's the password?
Sediment, chiefly eroded from the thrust belt itself, began to fill this depression or basin. Initially, the downward movement of the land surface, called subsidence, was occurring much faster than the sediment coming in could fill it up. As a result, a huge inland sea formed during the late Cretaceous, called the Western Interior Seaway. At its maximum extent, the Western Interior Seaway connected the Arctic Ocean to the Gulf of Mexico. The period of rapid subsidence when the seaway was filled with water is recorded by the deepwater Manco Shale. As the thrust belt grew and the basin filled up with sediment, the coastline closed in and the seaway eventually disappeared. This regression and basin filling event is recorded by the Mesa Verde group. Mesa Verde National Park is a national treasure because it tells a story of how an ancient civilization adapted and interacted with the land. It's part of the cultural heritage that binds the modern Pueblo people and Pueblo nations in New Mexico and Arizona. The park also tells an even older story, a geologic story, in which the artifacts are sandstone and shale. The great migrations and movements are shorelines marching across the continent, and it connects us not just to the land, but to the earth itself. Hey, thanks for watching. Check out some more videos and share them with friends and family. Take care.